got electrolytes.
What are electrolytes? Do you even know?
Welcome to Real Physics. The sun is not a plasma. Let me explain. I have argued in this video that the sun cannot be gaseous. Why? Because gases emit discrete lines of light and they could never produce a continuous spectrum as it is observed from the surface of the sun. Now in this video I have also addressed the question of a plasma because as a matter of principle a plasma could emit a continuous spectrum, but we're talking of the inside of the sun where there are very high temperatures, very hot dense plasma could emit a continuous spectrum. But you need to use your brain and you need to use your calculator. If you look at this, if you look at the Boltzmann distribution, you realize that only 1 in 1 billion atoms would be ionized. That means it would be capable of producing that continuous spectrum. Nonetheless, people continue to lecture me, it's a plasma. Plasma means electrically charged particles. But if you look at the comments of this video, it's a plasma. Don't you see it's a plasma? Don't you realize that all astronomers agree it's a plasma, it's a plasma, it's a plasma, it's a plasma? It kind of reminds me from...
The Brondo's got what plants crave. It's got electrolytes.
It's got electrolytes.
Brondo's got electrolytes.
It's got electrolytes.
What are electrolytes? Do you even know?
So I think it's a good idea we try to understand what a plasma is. Now let's unpack that a little bit and have a look at the energy level scheme of hydrogen. Well, people were arguing that maybe 1 in 1 billion atoms that would be sufficient to produce that radiation, but not only it's such a tiny fraction of the surface of the atoms at the surface, it's also if you look at this energy scheme, it's a huge amount of energy that these photons of the continuum would carry and that would burn your skin with ultraviolet. Now here's the problem. I mean, as I said, you need 13.6 electron volts to get out of the ground state of the hydrogen atom and you reach these intermediate levels. And well, if you have the electron ionized, if the electron is stripped away from the nucleus, then you have this continuum, but nonetheless if the electron falls back it would still produce a lot of very strong discrete lines like this Lyman alpha and so on. So it's already strange here. Now people came up with other ideas and they said maybe okay, we don't need that huge amount, what about other molecules, other ions? And there was the proposal of the H- ion, and indeed the H- ion has an ionization energy of only 0.75 electron volts because I mean this second electron is obviously not bound very strongly to the nucleus. The problem is here you don't have these extra electrons in the solar atmosphere to begin with because you always have to pay the very heavy price of 13 electron volts to strip it away from another atom. It's not that somebody sells electrons like ice cream in the solar atmosphere. You don't have all these electrons. Now if you look quantitatively, I mean, how could such a ionization occur? Atoms are bumping into each other, and if they have sufficient energy they would be able to strip away the electron. But if you look at the corresponding temperature, it's very easy. You translate that energy, that kinetic energy of 13.6 electron volts into a temperature and the result is 157,000 Kelvin. Okay, but at the sun we have 6,000 Kelvin. So I mean, the physics of all this is known very well. Planck's law tells you how a hot surface emits radiation. And now let's have a closer look at this. This is the formula. This is the Planck spectrum at 5000 Kelvin. And all what we have to do is plug that into a Mathematica code. Let's go. Here we are. And this is the Planck spectrum. I plugged in the formula. This is the Planck spectrum at 5800 Kelvin. And you see this is the visible range here. It's very nice rainbow colors are produced by that heat. That means if you have a surface of around 6000 Kelvin, you can produce that kind of light. But now look at what happens if I shift the temperature. Let's go to smaller temperatures. There are stars that have only a surface temperature of say 4000 Kelvin, and look, it's the total emission is very small. Once you go up to 6000, we have the normal star here. And there are two things to note here. The first thing is, look at the enormous growth of this area, that means of the total amount of radiation, if I go, say, from 4000 to 8000 Kelvin. And that's the law of Stefan and Boltzmann. And this law says the total energy radiated increases with the fourth power with temperature. That means if I go from 4000 to 8000 Kelvin, you would have a 16-fold increase of the total radiation. And the second thing to note here is that this maximum of the radiation, it shifts a little bit to the left. When I increase the temperature, you see here a maximum around, let's say, 600 nanometers. Then you have the 500 nanometers of the sun. And then if you go to higher temperatures, you see that the maximum gradually shifts to the left, to the shorter bluish wavelengths. Now, but we are still at 8000 Kelvin and we are very far from ionization, okay? So you noted that if you start here with 6000 Kelvin, you have around, say, that's 100 kilowatts per square meter per nanometers integrated here. If I increase the temperature, so I would have to adjust the scales, and that's what I do in this script. Here again, we start at the solar spectrum, 5900 kelvins here, and you're around 80 here. Look at this number, and now see what happens. 10,000 kelvins, already 3000. Okay, 20,000 kelvins, that would be 40,000 watts. Okay, it's 500-fold the spectral emission of the strongest line here, and we are far from ionization here. So if we go to 90, 100,000 Kelvin, 130, 140, 157,000 Kelvin, here is your ionization. Okay, and look at this. The spectral intensity is something 10 to the 9. Okay, so we have something like a factor of 10 to the 7. That means 10 million times stronger radiation. Okay, and not only it's much stronger, it's also in the very hard ultraviolet, almost soft X-rays. You see here the maximum wavelength of this radiation would be like 17 nanometers. It's incredibly harmful, and you don't want that. And you see the usual, what you see at the spectrum of the sun, it's practically nothing. Now, what does the standard solar model say? The standard model argues that this radiation we observe comes from different layers beneath the surface of the sun, and each layer inside the sun creates a Planck spectrum of these high temperatures, and the superposition of all these spectra coming from the inside, from the sun, eventually generates the 6000 Kelvin. That kind of sounds strange, but I mean, to savor the real absurdity of all this, there are two things to mention. The first thing is the intensity. As I said, I mean, you have a huge intensity increase if you go to higher temperatures, and if you go to the ionization temperature, you would have the total radiation 500,000 times stronger than it is observed. So you would burn the solar system out to Jupiter and Saturn with this enormous heat production. Absolutely impossible. The second thing is that you have a completely different spectrum. You're not emitting predominantly any longer in this visible spectrum which we observe, but in the ultraviolet, even X-ray. So it doesn't make really any sense. So, and then, I mean, think about, you need to combine all these spectra with appropriate filtering. How could such a superposition of so many spectra miraculously transform into the 6000 Kelvin spectrum what we observe? I mean, that would require a series of unlikely coincidences and fine-tuning. But the point I want to make here is that you would need an incredible filter of that strong radiation. You would need a filter that leaves through just, say, 1/1,000,000th part of that huge intensity. You would need a filter that suppresses all this hard ultraviolet and leaves through only what you like, what you see, the 6000 Kelvin radiation. And there is simply no mechanism if you have a gas, because you can imagine a strong, intense radiation going into a gas, and what happens? Okay, you would have scattering, that means the photons bumping into the atoms and getting deflected, like Compton scattering or whatever, but as a matter of principle, that does not change very much the wavelengths. So in order to transform that enormous heat, that enormous radiation from 150,000 Kelvin into what we observe, the 6000 Kelvin, you need condensed matter.
What you're saying is that you want us to put water on the crops.
Yes.
Yes, that's what I'm saying. You need condensed matter and you need a lattice. Only a lattice can transform that enormous amount of radiation that certainly exists within the sun into that 6000 Kelvin heat we observe at the photosphere. And by the way, that's how the photosphere looks. But that's a little bit another issue I will address in another video. One point I still want to make is that, I mean, if you believe in all this miraculous filtering, if you believe in this miraculous fine-tuning that all these Planck spectra of high temperatures might somehow be transformed into a 6000 Kelvin spectrum, there is still a big problem. You have still these very strong emission lines of hydrogen. I mean, whatever mechanism you postulate to get this smooth, continuous spectrum, you would have superimposed these Lyman alpha and so on, these very strong lines. How to get rid of that? There is no way, no possibility. Well, of course, there are a couple of other things to address in detail. I do this in chapter 3 of my book. One thing is the Saha equation, and well, the problem is that it's never been tested in the laboratory. It produces a lot of absurd results, but as a matter of principle, theoretically, it predicts that if you have very small densities, then you have a higher percentage of ionization, and that in principle could lead to a continuous spectrum. Then the core problem is, as I said, the filtering. It's called opacity. There is no such opacity at the photosphere, and for that reason people need to postulate somehow various substances that possibly could absorb light and so on and so forth. That's called Rosland mean opacities. It's a very absurd term because every spectroscoper would say that opacity is dependent on wavelength. So the concept of a mean opacity makes only sense for die-hard theorists. I mean, you can go into detail with these problems, but the key thing to understand here is if you have a continuous spectrum, it cannot be gas because a gas is discrete, and it's not a plasma because a plasma is too hot. It would burn us, it would emit in the hard ultraviolet, and the concept of a gaseous story does not make sense. You need condensed matter. Now, as I said, I described this in my book, and it's also very well described in Robitaille's paper. I invite you to look at this. Robitaille is the founder, I didn't mention it, that of this theory. He addressed, for example, the problem of stellar opacity in this paper, and you should also go to his YouTube channel. He has done amazing work in history and all details covering also this alternative model. And it's not to be dismissive about the standard solar model, but the problem is here, why did all these scientists go wrong? Because they desperately tried to fix the models because they didn't have a good alternative. Because the alternative, the liquid metallic hydrogen, was not known at the time, so history went the wrong path, unfortunately. And there is another aspect I'd like to mention. You observe that very often in modern science, that you have these huge efforts, these large collaborations, a lot of money, a lot of funding, big institutions, also big accelerators, and you create these models that tend to be very complicated and bypass the true real problems of physical reality. I think this is a part of modern scientific culture and addressed in my book, Make Physics Great Again. If you enjoyed the video, don't forget to like it, and if you're interested in fundamental questions, subscribe to this channel.